Okay, I'm free to start on it.
Yeah, okay, so thank you everyone for coming to the DIAS summer students presentations. First up we have Peter and Prathik, who worked with Denjo and Takaki on Bosonic and Fermionic matrix models. Take it away.
Okay, yeah, we were asked to introduce ourselves a little, so I may as well. I did theoretical physics and mathematics at Moody University for the last 3 years, and I'm finished now. And now I'm headed off to Bonn to do mathematics. So I'm a bit of a heretic. I'm leaving physics behind a little bit. Okay, so this is a talk in 4 parts. So there's 2 theory sections. So I'll talk about the gauge Gaussian model, which is like the simplest example of a bosonic matrix model. And then Prathik is going to kind of introduce the theory related to partition functions. And then I'll talk about some exact results and some of the kind of stuff I tried doing towards the end of the project. And then Prathik will talk about some of his results he tried doing and some coding that he did towards the end of the project as well. So I'll just jump straight into it. So this is just some recap. So like the simplest example is a bosonic oscillator. So this is just the Hamiltonian everyone knows, where you just have momentum and position. Technically, these are operators, but I just didn't put the hats on them. And we can diagonalize this by introducing creation and annihilation operators, okay? And after subtracting off the 0-point energy, the Hamiltonian can be written like this, okay? And as we know, the energy eigenstates are of this form, okay? Where this is energy 0 in this case, omega, 2 omega, etc. Okay, and there's a kind of analogous oscillator called the Fermionic oscillator, which is just the qubit system. The Hamiltonian comes like this, but instead of B and B dagger satisfying the commutation relations that A and A dagger satisfy, they satisfy anti-commutation relations. So that's what this curly bracket here means. Okay, and there's only 2 eigenstates now, just the 0 eigenstate and just the B dagger 0. And this is energy 0, and this is energy omega. And it's kind of a consequence of this and a reflection of the Pauli exclusion principle that there are no higher eigenstates, because that right there implies that B dagger squared is 0. Okay, so there can't be any more fermions in that state. Okay, so now onto the gauge Gaussian model, which can just be seen as a generalization of the bosonic oscillator. So instead of just the real variable x, we consider x to be an n by n Hermitian matrix, and then we take the trace. Okay, so it's reasonably easy to see that there's a global UN symmetry. So if we take x in this Lagrangian here and send it to u x u inverse, then this Lagrangian remains unchanged, right? Because x squared is going to go to x squared will go to u x u inverse u x u inverse. These will cancel, and the cyclicity of the trace will allow us to bring those next to each other, and they'll cancel off each other as well. Okay, so we'll just get the same thing back. Okay, and we can further complicate this model by introducing a gauge field and covariant derivative to turn this global UN symmetry into a local UN symmetry, which in this context just means that these unitary matrices are allowed to depend on time as well as x. And this is what the covariant derivative looks like. And all that happens is this derivative operator here becomes a covariant derivative. And then this Lagrangian is now locally invariant under UN. Okay, and we can talk about quantizing this model, which is worth doing because it's a little bit more complicated and I found it interesting. So one way of doing that is expressing x in terms of its real degrees of freedom. So I'm adopting the Einstein summation convention here. So n by n Hermitian matrices form an n squared dimensional real vector space, okay? And on that vector space, we have an inner product. If those are 2 n by n Hermitian matrices, the trace of their product acts like an inner product. So as we know from linear algebra, we can just choose a orthonormal basis with respect to that inner product. And that's what we've chosen the set of TAs to do here. Okay, and if we work with this and expand x in this way, then the Lagrangian simplifies to this form, which is just, it's just the bosonic oscillator again, but with a slightly more complicated momentum term, which looks like this. And the structure constants here satisfy that. Okay, so now we can just use the regular Euler-Lagrange equations because these are just real degrees of freedom. And the equation of the motion for the gauge field looks like this. So there's no time derivatives. So we just have this equaling 0. and it looks like that. And this is not dynamical, it's just a constraint because the gauge field doesn't change over time. If we, or to quantize it now, we need to switch to the Hamiltonian formulation, which we can do here, where PA is now, I should have written this down. That's what the canonical momentum is. And this term here, you see if you work it out, is just 0 from above, okay? So our Hamiltonian just becomes a collection of harmonic oscillators subject to this constraint right here. Okay, so we can quantize the Hamiltonian as normal, okay, by just sending position and momentum to operators, okay, that satisfy this commutation relation. Quantizing the constraint, well, it's 0. We just send position and momentum to operators again, and we just demand that the energy eigenstates of the unconstrained Hamiltonian vanish under the action of this operator. Okay, and the main goal of this project is, or the main goal, or one of the main themes, I suppose, of the project was to count the number of gauge invariant states for different size matrices. And I should say, you know, this can be generalized. I just quantized it for the case of one matrix, but you could have a collection of matrices as well. You could have K matrices, K n by n matrices. And typically the gauge invariant states kind of look stuff like this. So typically there's no free indices, is what we were saying. So anything else to say there? No, I don't think so. So I'll stop sharing and Prathik can share, and then I'll come back again. You might be muted, Prathik. Yeah.
Yeah, sorry about that. So yeah, just to introduce myself, my name is Prathik, and I'm studying theoretical physics at Trinity College Dublin, and I'm in my third year. So okay, diving into the presentation, I'll be talking about the partition function for the bosonic fundamental fields and be providing a basic derivation of sorts of how exactly these partition functions are derived. So note that via the path integral formulation, we have this particular formula for the partition function. Now, how exactly does this formula come about? Well, to very briefly talk about it, note that the partition function is generally associated with the following trace of e to the power minus beta h, while the time evolution operator in quantum mechanics is associated with e to the power of minus I h times t. So now note that by sending beta to it, that is basically complexifying time, one can see an association between the two. They basically become equivalent. And then by noting that by noting the path integral formulation from quantum mechanics, which states that if you have a state at position x naught at time t naught, and you take the inner product with a position xn at tn, then this is basically given as the integral sum measure e to the minus is. So from this particular thing here, you can note how exactly this formula comes about. Now from here, we note that the system that we are concerned with is that of the simple harmonic oscillator, although we do consider a covariant derivative, which helps us introduce gauge constraints into the system. And note that, and note that the XA over here are basically matrices. So it is clear that by introducing this S over here, what we basically have is a Gaussian integral, and one may formally integrate this to obtain this particular expression for the partition function of the bosonic fundamental fields. Now, note that since we have a determinant of this, well, it follows that once we know the eigenvalues of these operators, it is pretty straightforward to be able to explicitly obtain an expression for the same. Now, note that the omega over here is just the frequency of the oscillator and is a constant, and the mu is a constant that just comes from the integration measure. And the d tau squared here is what is called the Laplacian. Now, there are, well, many ways one can explicitly evaluate this out, but here we're going to consider a first order lattice discretization of the Laplacian. So note that we consider capital lambda lattice points, and I will basically do this out just to get a flavor of it for lambda equals 2. So note that we also impose periodic boundary conditions, And so the time is basically now in discretized units as a and 2a. And this implies, well, that at x of a, we label that position as x1. At x of 2a, we label the position as x2. But at x of 3a, since we have periodic boundary conditions, that goes back to x1. Now note that a first order approximation of the derivative is basically given by this formula right here. And basically squaring this formula and rearranging, you end up with this. And then representing that in matrix notation, you end up with this particular final form here. And know that this over here is what is a Laplacian. So now we're basically down to having to find the eigenvalues of this particular matrix. Now note that over here, we've only considered 2 cross 2 matrix, but more generally, we have this particular form for the matrix. And this is just straightforward algebra in going from here to here. Now note that using this particular property, which basically follows by considering the Taylor series expansion of the exponentials, we note that the Laplacian takes this particular form. Well, this basically follows from the fact that xn here is nothing but x of an. And so xn minus 1 would be a translation of x by minus a, and xn plus 1 would be a translation of x by plus a, which is what these operators over here do. And so, yeah, it's pretty clear how this is the Laplacian. And in the limit that a tends to 0, well, that basically becomes in the continuum the Laplacian. Now note that we need the eigenvalues of this, and it is possible to choose uniform gauge. And in that particular case, we have a translation invariant operator. And so we can use this particular ansatz. And well, basically here I'm trying to find out the eigenvalues. So I act the Laplacian operator upon the ansatz and obtain this. And here I've basically substituted for the covariant derivative, this particular formula here. And separating out the e to the I k tau, one can obtain the eigenvalues lambda k. Now we will do some further substitutions to this particular thing, where since the system is now periodic, it's clear that we need e to the I k tau plus beta to be e to the I k tau, implying this. And from here it's straightforward to know that this implies that k times beta is 2 pi n, or k is 2 pi n over beta. And yeah, so basically then we substitute that in over here. And also we note that we're considering Hermitian gauges. And as a result, it follows from the spectral theorem that there exists a diagonal representation of the same in terms of real eigenvalues, which is what we use over here. And the theta A and theta B are basically these eigenvalues. And hence, using that substitution again, you end up with these to be your final eigenvalues. Now, once we have the eigenvalues, then we know that the determinant of that matrix can just be computed as the product of these eigenvalues. And so that's how one can explicitly obtain a formula for the partition function. Although there also exist integral formulas to be able to obtain this partition function, and Dolan lists some of these. So this is the integral formula to obtain the partition function for one bosonic field, while this is the same thing for k bosonic fields, and the generalization is pretty straightforward. Now, how exactly we obtain this is probably out of the scope of this particular presentation. Basically, what one uses is zeta function regularization and Faddeev-Popov determinants to account for gauge invariant symmetries in the system. But yeah, we'll just take these expressions to be given, and we'll come back to computing those in my next section. But for now, let's move on to what is called as the Hilbert-Poincaré series. Now, note that mathematically, if we have a field K and let V be a graded vector space on top of that, then one can express the Hilbert series as a formal power series that takes this particular form. Now, note that in our case, the graded vector spaces are basically rings that consist of creation or annihilation operators. And yeah, so basically we are trying to, for each particular grading, the Hilbert-Poincaré series counts the dimensions of the possible, for that particular grading. Now note that, why is this important? It's not always possible to, solve the Schrodinger's equation or to be able to integrate some of those expressions, since they're really complicated at times. And so in situations like those, having the Hilbert-Poincaré series can help act as a generating function that counts the gauge invariant operators of the theory. So it can prove to be really helpful. Now, well, let us just, as an example, look at the simple harmonic oscillator system and, well, the possible states, allow solution states for different gradings. So it's clear that for a grading 0, you just have the ground state. And then for the grading 1, you can act upon with the creation operator Aij on 0. And for grading 2, similarly, and so on. And if you consider the Aij to be n cross n matrices, it follows that the dimensions of that particular grading is given, it goes as n to the 2i. And so then that becomes the Hilbert-Poincare series for that particular thing. Now, similarly, we can also have two types of creation operators, and this would basically correspond to theories that maybe include both fermions and bosons. So yeah, so again, similarly, we can, for each grading, you have like different possible solution states, and it's pretty straightforward to see how that implies this particular Hilbert-Poincare series. But however, as Peter already talked about this, we know that when a gauge constraint is imposed on the system, the number of allowed states are heavily restricted. As we saw that no more free indices were allowed in that case, and everything had to be in forms of traces. And so we can clearly see that here. So we start off with how the dimensions go as n to the 2i, but as soon as the gauge is imposed, now only traces are possible. There is no longer ij, there are no longer free indices. So you immediately note how the dimension reduces to 1, 2, and 3 from, it was going as n to the 2i. So we can see a heavy constriction of states, of allowed solution states. And a similar thing happens over here for, well, when we have two different types of creation operators, which is what I just listed out here. And yeah, and finally, to go to what the Hagedorn transitions are, well, note that once we have a partition function, it's pretty straightforward to compute physical quantities of interest, such as specific heats and energies, which basically amount to computing derivatives of these partition functions. However, there exist interesting cases when we compute these partition functions for really large n, right? So far, I mean, I will show it in a bit, but I think for the cases of for two bosonic fields, the maximum that people have been able to go so far, I think, is for n equals 7 and not higher than that. So it is important to note that there's a lot of structure to it when we go to the large n limit, which is what so these two particular pictures are from Professor Denjo's work, where he plots the specific heats and the energy. Well, over here, I'm just showing the specific heat for n equals 1 to 7. So one can note that how, as we go to larger n, there's a clear divergence that's approaching at this particular point. This particular point is what is known as the Hagedorn temperature. Now note that in the large n limit, as one goes to really high n, there's a clear discontinuity that one can see. Now, though I'm just showing this here like this, to maybe just give a brief analytical sense as to why this happens, we will just look at this particular analysis. So note that the SGG over here is basically just our action for the harmonic oscillator system, and integrating out the XA gives the effective action. Now, it is important to note here that the effective action is not the same as the classical action. The effective action also includes for quantum mechanical constraints in the system. And so it's basically a Legendre transform of the free energy. And well, that's just given as ln, sorry, right? So the free energy is given as ln of the canonical partition function, and the effective action S effective is the Legendre transform of the free energy. And so it is clear that basically once we have the eigenvalues, it is possible to compute the S effective for the particular system. And once we have that, we use these particular substitutions. These are basically functions where the theta I correspond to the eigenvalues of the gauge matrix. And yeah, and then you substitute that in here to obtain this particular expression finally. Now here it is important to note that this particular system has a minimum at 0 as long as 1 minus d times e to the power minus nm beta is greater than 0, right? Now, the second that this goes to a negative value, this minima then becomes a maxima, right? And so the critical value at which this changes is what indicates a phase transition, which is the Hagedorn transition. And to be able to obtain that critical value, one can just, well, set this and m beta to 0, and note that on rearranging this, you obtain this where beta h is nothing but 1 over th. And so this is probably an analytical side to how, or what suggests the Hagedorn transitions to occur. Let's stop sharing now and let Peter continue the next part. Sorry.
Okay, let's start again. Okay, so I can't say everything that there is to say about partitions and Young tableau and symmetric polynomials. So hopefully I'll just be able to give like a flavor of what's involved. So there are exact results known for the case of one fermion and the case of one boson, or bosonic fields and fermionic fields, I mean. So I'll just kind of illustrate how that happens, basically. So there's kind of a correspondence between things called partitions and tableau, or Young tableau. So a partition is just a way of partitioning up an integer, essentially, okay? And you do it in kind of a decreasing order with the largest integer first. So this would be a partition of 6, 3 plus 2 plus 1, and corresponding to that, there's a Young tableau. So you have 3 boxes at the top, 2 boxes, and then 1 box, 7, okay? There's 5 boxes, 3 boxes, 3, that's a partition of 3, and you just have 3 boxes down like that. Okay, and a notion that we'll need is a notion of self-conjugate partition or self-conjugate tableau. So this is self-conjugate because if you flip it along this main diagonal, you get back the original tableau. These aren't self-conjugate, okay? Because if you flip those along their main diagonal, you don't get back the original tableau. And the kind of thing I found interesting was that counting gauge invariant states with energy n omega is kind of the same as counting subsets of partitions of n. Only in the case, or only so far I've discovered, in the case when it's one fermion or one boson. This was something I found quite interesting during the project. So I'll just briefly mention what a symmetric polynomial is as well. So a symmetric polynomial is a polynomial that's invariant when you permute the variables. So that's going to be symmetric if you swap x and y, it stays the same. Same with this one. And one more fact we need is that this right here is an inner product on n variable symmetric polynomials. So it looks a bit weird, but this kind of, I suppose, measure would be the correct word. Shows up a lot when you're evaluating these partition functions, and it turns out that it's an inner product on n variable symmetric polynomials. And in fact, a particular family of n variable symmetric polynomials called the Schur polynomials are orthonormal with respect to this inner product. So that's a kind of important fact. Okay, so the case of one bosonic field is worked out in Dolan's paper. I think Prathik mentioned it a moment ago. So this is the integral we have to evaluate, okay? And how we can do that using the techniques I just mentioned is you can expand this product out using the Cauchy-Littlewood formula, okay? This isn't quite the Cauchy-Littlewood formula, it's just kind of a consequence of it, but we see we get a sum over partitions where the number of parts is less than n, and parts just means the number of rows of the partition, right? So I'll just scroll up quickly. This has 3 parts, 2 parts, 3 parts, okay? So we're saying that, you know, this product here can be expanded like this. It's a sum over all partitions with at most n parts, okay? And it turns out for each partition, there's a corresponding symmetric polynomial or a corresponding Schur polynomial. Okay, so hence we get that this partition function here can be written as this sum with this inner product term here. And this is just going to be delta lambda lambda, so that disappears. Now, if we look at this for a moment, sorry, I should have said the absolute value of lambda just means if lambda consists of 10 boxes, then the absolute value of lambda is 10, okay? So this sum right here is going to count the number of partitions of n with at most n parts. So the coefficient in front of Tn is going to be how many partitions there are of the number 10 with at most, let's say if n was large n was 3, at most 3 rows, okay? So that's what this sum here counts. And it's a well-known result from the theory of partitions that the generating function for the series here is given by that. And Dolan discusses this in a bit more detail in this paper. So this is kind of an exact result. Obviously, if you wanted to actually count the number of gauge invariant states for a particular energy level, you would have to expand this out and stuff, but it's a nice closed form for this partition function here. So something small I did during the project was just copy what Dolan did in the paper, but for the case of one fermionic field. So in that case, the partition function looks like this. Okay, this product term can again be expanded into this form. And I should mention lambda star corresponds to the partition conjugate to lambda, or the tableau conjugate to lambda. So lambda here is the sum over partitions with at most n rows and columns, okay? So when we throw this expression back into there, we get an inner product, but now we'll have a delta lambda star. So we see we have partitions where those two things are equal, which is the self-conjugate partitions. So this sum now is counting the number of self-conjugate partitions with at most n rows and columns, okay? And again, it's a well-known result that that series right there is in fact equal to this. So again, we have a kind of exact result, but now in the case of one fermionic field. Okay, so I found this quite nice. So what I tried doing was like finding an interpretation for, let's say, the two boson case or the two fermion case where, you know, T10 would count the number of states at the 10th energy level, and somehow that would correspond to like some subset of the tableau with 10 boxes. But that didn't turn out to be possible. So I'll just say what I was doing. So for two bosons, the results are known up to n equals 7, and this is in this paper here. So like I just mentioned, I tried using similar tricks to the ones I just described for one fermion and one boson to evaluate the two fermion case for general n. Because if you look, these are the results for two fermions. Like, well, I've left out a bit here, but they're palindromic polynomials and they're quite symmetric. And I thought, okay, maybe this right here is counting, you know, some subset of partitions of 4 and stuff like that. But that's not possible, because if it was, then, you know, that would be some number of subsets, or that would be some subset of partitions of 1, and there's only one partition for 1. So yeah, that was what I tried. So that's the end of my little talk. So I'll pass it back over to Prateek.
Yeah, okay. So right. So here I talk about some of the explicit results that I computed during the during the internship. And so yeah, so here is the case for n equals 3, k equals 2. So I already showed you the general integral formula for the bosonic field, for the k bosonic field system. And so yeah, this is basically just expanding out that formula. And then from here, note that the integrals over Z1, Z2, or Z3 are basically, the Z1, Z2, and Z3 are basically complex variables. And these integrals are over the unit circles in the complex plane. And so computing these integrals, well, theoretically, it's always possible, because they just amount to computing residues of these, computing the residues of these polynomial expressions, which is a pretty straightforward exercise. But it's just that they become extremely cumbersome as we go to higher n. For example, just for the case of n equals 3, you can note how, large the polynomial expression is. And yeah, so, well, basically, just to briefly go through it, you have this particular expression, and we try to identify all the poles over the integral Z3, and then which are basically listed out over here, and then using the integral expression, and then basically using the residue theorem, we obtain this expression. And then we similarly do the process for the integrals over Z2 and Z1, and eventually obtain this particular partition function. Next, I also computed the partition functions for the case where now there are both bosonic and fermionic fields. Dolan's equation 2.38 gives you this particular formula, for the case when there are both bosonic and fermionic fields, well, to be precise, K bosonic and K bar fermionic fields. And I evaluate this for, I obtain a general formula for them. So compared to the previous expression, this one's more straightforward in the sense that for the case K greater than K prime, the only poles are at Z equals Tj. And so basically then just using the residue theorem, you get a sum of all the residues, which are given by this expression. While for K less than K prime, what happens is that you get extra factors of Z in the denominator. And so then you need to also account for the poles at Z equals 0. And that is where this extra term comes in when we compute that. And yeah, so as I stated before, I also tried to compute and plot the energies and specific heats for for basically these systems that we just talked about. So this is the case, this is the energy versus the temperature plot for the n equals 3 single bosonic field. And this is the specific heat for the same. And this is the energy versus the temperature for the K bosonic field case for K equals 2. And this is the specific heat. If you note that this seems to match with what Professor Denjo had in his work. So the n equals 3 case here, I think, is the yellow one. And we note that we have a similar shape of the graph here. And as I already explained, how the Hagedorn transition arises is when we compute these for larger n at the Hagedorn temperature, we basically start observing this diverging trend, which then eventually is what suggests the phase transition. Finally, I tried to also compute these physical quantities of interest via the Metropolis algorithm. Well, to just briefly state what the algorithm does is that it is essentially a Markov chain producing algorithm. That is, the next item depends on the position of our current item in the iterations. And the algorithm basically aims to reproduce samples from a target distribution, which in our case is this. So note that for our particular system, the gauge Gaussian system, the action is given by this formula over here. And so using this formula and starting off by a pseudo random assignment for the sample of parameters, where I used random.uniform, the random.uniform class from Python to basically assign initial random values to the thetas. Well, to be precise, I solved the system for n equals 3 and n equals 3 and d equals 3. Note that we start off with an initial random value for each of the thetas. And then based on what is called the Metropolis check, which is basically that e to the minus delta s is greater than equal to 1. So based on this check, if this check was true, then we updated the thetas according to this. While if it was false, we updated the thetas according to this. And I did this for r equals, well, I think that's, yeah, well, basically that many number of iterations. And I obtained this particular graph. So note that this here, so the different colors here basically correspond to the different thetas. So theta 1, theta 2, and theta 3. So you start off from these random values that are chosen between minus pi and pi. And then the algorithm does its work. And then it tries to eventually arrive at different points for these thetas, which now these values are basically samples. We expect that these values are then samples from this particular target distribution. So yeah, so that was what we did. And it might also interest to note that there seems to be a lot of autocorrelation in these graphs. And so one way to kind of reduce that would have been to implement the hybrid Monte Carlo method. And yeah, so that would be something that we can do further in this direction. Also, in terms of explicitly computing the energy for, say, a particular case, this is the formula where we sum over where we sum over each sample. Now, a particular sample basically involves these end values for the thetas. And I do this for the case of n equals 20 iterations. So I basically collected 20 samples and used this particular formula to evaluate an energy. Now, doing that using the code, I got 81.96. While doing it explicitly using the partition function, I got 100.72. Well, you can note that the values are not quite close enough, but I mean, they're fairly close enough, but they may be not the exact same thing. And one particular reason for this is that these after all happen to be statistical methods, and to be explicitly able to confirm the results, we would have to implement errors. One of these errors is called the jackknife error. And so that would be something that I would like to work on in the future as well, and try and improve, like, yeah, improve the code. But yeah, so that's my part. Yeah.
All right. Thank you very much, guys. That was a lot of different stuff that you covered there. I don't know if there was any area of maths that was safe from that project. Yeah, does anyone have any questions? We'll block out five minutes, I say, from now, before moving on to the next one. I had a couple of questions anyway. Maybe I can go first. I think it was in Peter, your talk where you said, oh no, sorry, it was Prathik. You were talking about integrating out XA to get the effective action. And I think I was just missing something at that point. It was the effective action for, it was like as a function of theta, right? At that point.
Mm-hmm, right.
So that's the effective action for the gauge field, or?
Oh, well, let me just share my screen and I can show it. Right, so this is basically the gauge Gaussian model, right? So this is the action for the gauge Gaussian model. Now note that the gauge constraint is basically imposed via the covariant derivatives. Now in going from here to here, we basically go via, so this basically over here is supposed to be the effective action. And how exactly we compute the effective action, as I explained, was via this formulation here. So the free energy is given as the logarithm of the canonical partition function. And we already saw in the beginning of my presentation how you compute this partition function by computing the eigenvalues of the Laplacian operator. And so once you have that, then you basically, so if you can, so if you can notice the structure of these eigenvalues, right? The 2 pi n plus theta over lambda and stuff, right? So, well, once you have these eigenvalues, the determinant of the operator is basically a product of these eigenvalues, right? So what essentially is happening is you have that, so you have that the partition function is a product of the lambda n eigenvalues. And when you take the logarithm on both sides, what happens is this pi, the product, converts into a summation. And so then you have ln of z is equal to a summation over log of lambda n, which is something that you can note over here, right? So you have the summation over the eigenvalues. But even in coming just here, you go from here to the S effective action by considering a Legendre transform of the free energy. And so eventually when you do all of that, you end up with this.
Sorry, Prathik, just to correct, there's no Legendre transform in this.
Okay.
It really, all you've done is you've taken you've done the sum over the eigenvalues of the Laplacian, and you're left with this as the logarithm of z. After eliminating the x's.
Okay.
Just to
So are there two fields here to think about, the XA field? Or this is the way I was thinking about it anyway. And that was what you were saying you were integrating out.
So what I mean by XA over here is that you can have different XA, right? You can have X1, X2, X3, and these are basically just matrices. But over here, well, I just, yeah, so
perhaps I can just say it for 1 second, Prathik, just so, because it really is just integrating out the XA. You integrate out the XA, you simplify the expression once you've integrated out the XA. You still have to do the integrals over the gauge field, which amount to the integrals over theta.
Right, okay, yeah.
Before the intermediate expression is when you take the log of the intermediate expression for the partition function without only integrating over the x's, you get S effective.
Yeah. Okay, doke. I think that clears that up for me. I noticed as well that you, in one of your later diagrams, Prathik, you had like, you mentioned the Hagedorn transitions, and yeah, this one here in the bottom right. Can you just say again what it was you were, so, you know, you've drawn over that diagram with these red lines. What did they correspond to, and how were they related to the Hagedorn transitions?
Like, I was just showing this basically. So I was just drawing. So the particular curve that I have corresponds to this yellow line over here for the case n equals 3. But if we, well, ended up computing these partition functions for a higher n, then that was what I was basically drawing out, like just these other curves for the higher n.
Okay, yeah.
Derivative of them. And eventually when you approach the large n limit, as I showed the analytical part here, you end up with this divergence, which is supposed to be the Hagedorn transition in the case of these transitions.
Okay. Is there a quick physical summary of what the Hagedorn transition was about? Like in terms of what you might see in an experiment or something? Open question as well for Denjo, you know.
It's confining deconfining transition in QCD.
Okay.
Question.
Yeah.
Congratulations to both Peter, and in this Olympic times, this was a relay where nobody dropped the baton. My curiosity is, where is the Faraday-Popov contribution? You have a gauge symmetry, and it's somewhere in there.
Well, yeah, so the Faraday-Popov determinants, well, they basically come in while trying to compute these expressions. So note that due to the gauge symmetry in the system, right, when the gauge symmetry basically implies an overcounting of the field.
Right.
Yeah, overcounting, and to account for this overcounting is when we include the Faraday-Popov determinants, and then you basically simplify that expression to obtain these particular integrals here. Well,
because one aspect of this project that kind of intrigues me is counting how much overcounting. You're counting the number of states that are gauge. Sorry to be. That's
we
what I am.
Just the Faraday-Popov determinants are effectively those van der Waals. That's the residual effect of them, those van der Waals.
Oh, there you go. Okay, thank you.
Cheers. I think it's probably time to move on to the next talk. So yeah, we can ask more questions and everything at the end. Thank you again to Prathik and Peter. So I think William, you're up next if you want to share your screen.
Okay. So hi everyone, my name is Williamronaine. I'm just going into final year of mathematics and physics at University College Cork, and I'll be giving a talk on space-time topology change. So let's go through. I'll first just do a quick introduction and describe roughly what we're doing. And then I'll do an overview of the mathematical tools that are used in the construction, and I'll go through the results that we got. So a space-time topology change is something that happens when there's a topological change in the spatial topology, spatial slices of the topology as time progresses. So you see in the diagram here, you've got, this is called the trousers topology, which is the classic example of this. At the start, you've got if you consider time being going along the vertical axis, then a spatial slice would be a horizontal cross section of this. And at the start, there's 2 copies of the circle. And if you go past here, you've got 1 copy. So they're topologically distinct. So that's an example of a topology change. And it is it's believed that incorporating this idea of topology change is going to be necessary for a complete theory of quantum gravity. So that's the motivation of studying it. And just the formal definition is it is a topology change if you can't write the manifold as some spatial manifold M cross or cross time. So you can't do that here, because if you write this as just a circle cross time, you'll get a cylinder, but clearly it spits out here. So there's a change in the topology. So that's the basic idea. Now the topology we're going to look at occurs in the pair production of black holes. It's described in the papers by Dowker and Syria and Garfinkel and Strominger above, and they get a particular topology out from solving equations of gravity coupled with electromagnetism for something called a Wheeler wormhole, and it is a pair of oppositely charged extreme Reissner-Nordstrom black holes that are identified at their throats in an electromagnetic field. Won't worry about that, but the basic idea is that they solve the equations and they get out a particular topology, which is that it has initial topology of R3 and final topology of S2 cross S1 minus a point. So it's a sphere across a circle with a point taken out, so it's no longer compact, the idea. And so main point here is that if you try and solve equations for the pair production of black holes, I think it's in the background of magnetic field, you get this topology out of it. And so what we're going to do is look at that topology, but with a much simplified geometry without any of the actual electromagnetism or anything like that, which could be used, for example, to simplify computations for quantum field theory and so on. So that's the motivation for it. The basic idea, you can see with this diagram here, is that you've imagined two black holes, which are just represented by spheres, two spheres that is constructed that appear at the origin, and they move apart and travel along the z-axis with a velocity v. And initially the topology is R3, and then, well, yeah, finally the topology is the S2 cross S1 minus a point, because the idea is that you identify the boundaries. So these 2 points here in the new manifold are the same. So you identify these boundaries, and then you basically you glue it together along these surfaces here, so that I guess technically you could go in here and then come out across here, and you identify points z and minus z. So at the start, these 2 points here would be identified, and then as they move apart, eventually there's a kind of symmetry across the z equals 0 plane, if you like. And that's how you make the topology, basically. So you identify these surfaces and then essentially glue the manifold together using something called a connected sum. It's a bit difficult to visualize in 4D, but the idea is that you can go in here and come out here. And so the tools you use to do that is something called a smooth connected sum, and I'll just briefly go through that because it's important for the result we get at the end. The first thing you need for it is a thing called a Causal neighbourhood, which is a kind of, it's a neighbourhood that's generated by the flow of some vector field from the boundary of a manifold. So you can see it. This is a diagram of it. So if this is the boundary, the idea is you flow in along the direction of some vector field for some time, and that creates this basically a kind of a coordinate system for some neighborhood of the boundary. And there's a bit more technicality. You have to restrict the flow appropriately so that it remains bijective, but I'll forget about that. But the idea is you start at some point in the boundary and then you flow for some time. And so the 0, 1 here is the time you flow for, and this is the point in the boundary. That partial m is the boundary of m. The reason we do that is that it creates a good method for gluing manifolds together. So if you can see down at the bottom, you have two manifolds m and n, and they have a boundary, and they've got this Causal neighborhood thing. And the idea is basically you identify the boundaries. So you you create a new space where these boundaries are the same points, and you do that with a particular diffeomorphism H. And then if you almost imagine, you know, taking these two bits here and just slamming them together at the 0, you get this thing, which is -1, 1 across the boundary. The idea is in the new manifold, the boundary of n and the boundary m are the same points. So they kind of merge into each other, which you can kind of see here. That's a general thing you can do in topology without worrying about the neighborhoods, but to actually have functions and a smooth structure, you need to have charts for the neighborhoods of the boundary. And the way you do that is, if you consider this -1, 1 across the boundary, if s is less than 0, you would, so you're in this neighborhood of the boundary. If s is less than 0, the coordinates is you flow into the left of m for some time s along this pre-existing collar neighborhood thing, and if s is greater than 0, you flow into n. So that's given by this function here. Like the reason so if you're just in m, you can just use the charts for m. If you're just in n, you can just use the charts for n. But if you're going across, you need to have some way of doing that, and the way you do it is this. So that's the idea of that. Now the key point here is that you'll notice there's a -s here. So at this boundary where we've glued the manifolds together, there's a kind of an absolute value thing happening, which means significance of that is that functions that are smooth on m and n, when you glue them together, aren't necessarily going to be smooth, because there's this kind of a jump that's happening as we go across here in the coordinates. That's the main point. And so if you want to consider the behavior of functions as they cross the boundary, you need to consider how they behave when they're kind of put in the coordinate representation given by this -1, 1 across the boundary thing here. So that's the only coordinates that work going across the boundary. You have to use these. That's the significance of that. So I'll just move on to what we're actually doing. So we want to identify the surfaces of two spheres, basically. So we describe that by the 0 set of this function. This is a sphere of radius big R with center VT. So the center moves along the z-axis with velocity v, and that's parameterized by this function here. And there's one for z less than 0, one for z greater than 0. So there's two spheres. And then we can, in order to come up with our collar neighborhood thing, as I described just there, we need to come up with coordinates. So we just use these kind of cylindrical coordinates for the interior, or for the surfaces of those spheres. So this is just the coordinate system here. This doesn't really matter. This is just a way that the technical stuff we're using to get to construct the connected sum. And so then what we do is we remove the interiors, or the world volumes of these spheres. So you remove the interiors of the spheres from the manifold, and then you basically glue it together along these surfaces. So that, I guess, in the new manifold, this point here is actually right, points here are actually right next to this point here in some sense. So it's kind of being glued together. And the way we do that, I'm not going to go through the computations, but we do it with that method described above, where we come up with these basically coordinate systems called collar neighborhoods, and we glue those coordinate systems together, and we get a coordinate system that'll work for points that'll go through this surface. And this is just the final result of the coordinates we get. So this isn't that important, but this function, the -1 there doesn't matter. It's just, this is from the notes I was using. But these are basically, it's kind of like a chart or an inverse chart for the manifold that will allow us to look at the behavior of functions as they go across that identified boundary. And so if you, this is, well, because if you look at s equals 0 here, this point will be the same, except this will be, this is minus r cos phi plus v tau, this is r cos phi minus v tau there. -1 times each other, but in our new manifold, the idea is that these are the same point. They're identified. So that's where that difference comes from. So this is a coordinate system that allows us to go through the boundary, which is the point. And then this manifold then has, the idea is that it has the topology S2 cross S1 minus point, which is the same topology as you get from the pair production of black holes. That's the reason we've done this. And the thing we want to look at is how the metric looks in these coordinates. So how it looks as it goes across this boundary thing. So the standard flat Lorentzian metric we get in cylindrical coordinates is given by this. And if we just calculate the metric in the Causal neighbourhood coordinates using the standard pullback formula here, this is for the induced metric. This is the formula we use, and we use the function, use this function to compute it. So that's the point of this. And this is the result basically. So this is the matrix of components of the metric, and most this is just all these sines and tans. This is just from the coordinates we've used, but the important point is that there is absolute value terms, and these absolute value terms come directly from this thing here, because when we're going through here, we kind of have to switch directions at this point, and that creates this kind of not a discontinuity, but a non-smoothness in the charts basically. So normal smooth functions aren't going to be smooth in the new manifold. And so you have these absolute value things. So the metric is continuous, but it doesn't have a continuous derivative. And so one thing you could draw from this is that the scalar curvature, for example, which will include terms with second derivatives of all the metric components, it'll have terms of this type, the second derivative of an absolute value function, which is roughly speaking a delta function. So there will be kind of delta functions in the scalar curvature. So you could loosely call that a kind of a singularity at the point where you teleport from the surface of one sphere to the other. So there's a kind of a singularity in the curvature that comes out from gluing these two metrics together, if you want the metrics to be flat on either side. Now that where you could rectify this is by adjusting the metric close to the boundary, which would, so having some other metric that would then cause the metric to transition smoothly across the boundary. And that's something you could do. One thing that could be done in the future is seeing what metrics will actually rectify some of these problems where you've got delta functions appearing in the scalar curvature. So I think that's it. Yeah, thank you for listening.
Right, thank you very much, William. That was really nice formalization of some of those ideas in topology change. Are there any questions? I was gonna. Oh,
I think Faye has a hand up.
Oh, right. Yep. Faye, are you able? You're unmuted. You're able to.
Yep.
Speak. Sorry. Yeah.
Thank you for a nice talk. So just to clarify, I got a little bit lost at the end. So the metric that you're displaying there, is that a metric on a Lorentzian metric on a topology changing manifold, a 4-dimensional manifold, which has one boundary, which is R3, and then an initial boundary, which is R3, and a final boundary, which is S1 cross S2 minus a point. Is that what that metric is?
It's supposed to. I think so. I'm not entirely sure, to be honest, but it's supposed to be anyway. But
it's the metric on the later half of that topology change. So it's just the metric for when the spheres are the balls have been removed and you've identified the edges of the spheres. What you would get if you did that color identification that William was describing. So it's not got the R3-ness from before the topology change. So you know, this won't be the this metric is only valid in the color neighborhood, which only exists when there are these spheres that you've removed or balls that you've removed and the surfaces that you've identified.
So is the topology of this, I mean, does this have a time symmetry? I mean, is there
well, yeah, there's time in this. Well, I see that it's in different coordinates because of this third. I think the arrangement of this is there's st, so time is the second coordinate in this. So that's the time component there in this particular one.
There is a theorem, no, that Lorentzian covariations don't exist.
Yeah, by Garroch. Is this what you're?
So
yes. So we're allowing ourselves at least one point, if not maybe more points, where the metric becomes degenerate, and then we are essentially excising that point and trying to do the best that we can with what remains, or trying to define a sort of coherent or self-consistent quantum field theory on top of the remaining space-time. And space-time in quotes now, because you know it's got these degeneracies and we've removed these points and everything. So
can I try and understand a bit more? So when you say it's the upper half of the cobordism,
yeah,
is there a parameter which describes how these two excised balls moving apart?
Yeah, the V, do you mean like how fast they're moving? Or that was the velocity with which they were moving apart. And
okay.
the big R is the radius of each of the spheres, and there'll be a point in time where they're, you know, overlapping, and that will affect the region of validity of some of the coordinates in this expression. Because if they're overlapping, you won't be able to take, you know, theta or phi or whatever too far, or else you're talking about points that don't exist in the.
Okay, but it seems to me that while they're overlapping, wherever they're overlapping in this space-time, the three-dimensional spatial topology is R3 still. And it's just, it changes, the topology changing point or Morse point or whatever occurs when the two spheres just touch.
Yeah.
The two excised balls are just, you know, they just intersect in a single.
Yes, yeah, exactly.
point.
Yeah, once they've
okay,
separated, then you've got the different one.
Right. So, but is this metric then covering all of that? It covers some parts of this metric. This metric describes some four-dimensional portion of space-time where the excised spheres are overlapping, and therefore the spatial topology is still R3. And it also covers some regions of space-time where the excised balls have come apart now, and the spatial topology is then S2 cross S1 minus a point. Is that?
Yeah, I think if we take into account the restrictions on the coordinates, you know, where they're allowed their ranges being a function of time, say the time coordinate, then maybe you could make this metric cover the part of time when the spheres are overlapping to the point in which they actually break off, and include both those two regimes, say, in this one metric. But then you've got all these separate, you know, piecewise conditions for the coordinates ranges at the side as well, not just the metric expression on its own. Does that sound reasonable?
I think so. Oh, and yeah, so then just the final question, which I mean, I don't expect William to answer it, but it's a question to think about. So what are the coordinates then of the topology changing moment? So that's some event in space, it's some point in space time, which may, it's singular, as Ball points out. So the Lorentzian metric is degenerate there. It's not a Lorentzian metric there, but still you can, there'll be some coordinates for that point. The question is, where is it? I'll leave that question for William.
Yeah.
to think about. We don't have to stop.
I think
all
that's
that now, but
possible to answer in that, the phi coordinate is just the angular coordinate. Will, is the phi coordinate the angular coordinate around each sphere, or is it an angular coordinate?
Yeah,
from
the
origin?
phi, so there is time in the phi as well. There's time, and you see it's supposed to be like cylindrical coordinates around the cylinder that's cut out by the spheres. That's just what I use to calculate it.
So
there is time
does that mean that phi equals pi, the point that's on the inside of the sphere, that would be closest to the other sphere, or is phi equals 0 that point?
The point that they pull apart, that would be on the z-axis, I think.
Yeah.
Which would correspond to or equals 0, which would be phi 0. Yeah, I think.
Okay.
Can I make a quick comment, please? Because I have to leave now.
Oh, sorry. Go ahead.
It's a short comment. I think that if one is doing quantum physics, I think these problems can be overcome, because the topology of the manifold is coded in the standard quantum mechanics, the domains of the operators, for example, the time evolution operators. And so happens that this domain is a module for example, if it is R1, the underlying manifold, it is a module for smooth functions on R, can be started like that. Okay. So by changing the domains of the operators, one can, for example, go from one circle to several circles. At the quantum level, it's not a classical situation at all. And you will also get superpositions of topologies to try to reconstruct the manifold by using this Gelfand-Lamach, this duality theorem. Okay. We have a paper on this long ago with Beppe Marmo and some others. So these problems, I think this is the correct way to do it, not manifolds, because manifolds are constructs which come from some algebras. Where are these algebras? They are, I believe, at least I think I can prove that they are coming from the domains of the operators is a Hamiltonian. And what is the algebra, say commutative algebra, you can realize on them, okay, without leaving the domain. So there is a completely different approach to all these problems. It's what I think. Okay, there is a paper long ago. We had a paper on this. Okay, yeah. So basically, with Beppe and a couple of others, Bimonte, Beppe, and some others. Okay.
Yeah,
okay.
I think I've come across that one.
So this is a different. So I have to leave now. This is a very interesting topic, but
yeah,
I have to leave now. So bye. See you then.
Right.
Bye.
Thank you, Val. I think that's all the time we have. We can save any other questions and discussion to the end. So thank you again, William, and let's move on to the final talk. All right, take it away.
Hi, I'm Saoirse. I study in NUI Galway, and I studied mathematical science, and I'm going into my final year. So the title of our project is Black Hole Entropy in Causal Set Theory. What we did was we investigated causal structures of horizon molecules, and our main objective was to find a counting prescription of the microstates that would correctly scale with the entropy. Yeah, so the outline of this presentation, I'll give you a bit of background information, and then I'll go through the boson sprinkling process, and then Ben will go through horizon molecules to give you a definition and a few different structures, and then Tianyu will go through a few counting methods of what we tried, and then we'll summarize at the very end. So in causal set theory, we're assuming that space-time is discrete. Okay, so if you look here at at the diagram, on the x-axis we have space, which is in light seconds, and on the y-axis we have time, which is in seconds. And these points here just correspond to like space-time events. And if you look at the middle point here, you see dotted lines going through it, and the red lines there correspond to light lines. Okay, so everything that's within the red lines are causally related to this point in the future, and everything that's within the green lines are causally to its past of this point here. And then the points that are outside it will cause space-like. And so our goal was to determine structures in causal sets that give approximations to continuum quantities. And yeah, by doing this, we looked at horizon molecules and the ways we can count them. So if you look at this diagram here, so this is the causal set, and you can see that it's bounded in this diamond, and these lines are light lines, and they're at 45 degrees because of the scaling. Yeah, so the probability of the point being sprinkled in each region only depends on volume up to a density constant. And yeah, so the boson distribution is given by this equation here, and we used it because it gives uniformly randomly placed in space-time points. And yeah, so it's a good time to mention that we're working in flat space-time. Yeah, and I'll let Ben continue on.
Thank you, Saoirse. My name is Ben Graham. I've just finished my penultimate year in theoretical physics at UCD. And to pick up from where the point Saoirse was making there, the reason for the Poisson sprinkling is, as opposed to say a uniform lattice, is because a uniform lattice isn't uniform in all frames. So we require this sprinkling to kind of get around that and satisfy the volume requirement. So I'll be discussing how we worked computationally with the causal sets, describing the horizon molecules Saoirse mentioned already, and introducing the black hole entropy, which is the focus of our talk. So to work more efficiently with the causal sets we calculated a couple of adjacency matrices. The first of which, the causal matrix, we get is a matrix made up of zeros and ones, where the row and column indices correspond to points that have been sprinkled in our space-time diamond. So if a point J is to the causal future of point I, it returns a 1, and I've included a plot here on the left of all of those relations. So we have a point on the far left that has nothing to its causal future or past, so it doesn't have any causal relation to any other point, and then the more central points have a lot of causal relations. So we were able to use this causal matrix to calculate the link matrix, which has a tighter restriction on giving a 1 for a given entry. A point J has to be the nearest neighbor of a point I. So that means that there needs to be no intermediate points, no point K such that it's to the causal future of I and to the causal past of J. So the two diagrams here, I have the link matrix relations plotted on the right, and it's the same sprinkling. So the causal matrix plot is a lot more dense with these links. We sorted the points by time coordinate before we generated these matrices to obtain a natural labeling. So both the causal matrix and the link matrix were upper triangular, which helped when we were able to extract a sub-link matrix depending on the region within our space-time diamond that each point lay in, which we'll see now when we define the horizon molecules. So we've been discussing these horizon molecules, and as Saoirse introduced in the background, a common goal in causal set theory is to determine structures in causal sets that give approximations to continuum quantities. So as proposed in Barton et al., this structure that we're working with here is a horizon molecule, which goes on to be an indicator of the surface area of our black hole in this case, in our toy model of a black hole. So a horizon molecule is made up of a pair of elements, P minus and P plus, with P minus laying in this bottom right region below our surface sigma and our light-like slice H in C minus minus. And then our P plus point has to lie above our light-like slice H and below our sigma surface in C minus plus. From our defined link matrix, we extracted sub-link matrices, and we're able to use that and use vectorized functions to efficiently calculate candidate P minus and P plus points based on the requirement that they need to be maximal in their regions. And it's worth emphasizing at this point that the horizon molecule is the link. It's the pair of the 2 points. It's not either of the points P minus or P plus. So we've included a few plots here of horizon molecules in 1+1 spacetime. So on the left, we have one horizon molecule, one link from the orange P minus point to the green P plus point, with sigma being represented by a blue line here and our light-like slice, as Saoirse mentioned, being 45 degrees in this plot, labeled H. In 1+1 spacetime, we found that it's only possible to have one P plus. If there was an additional P plus, at least one of the P minus points would see both of our P pluses, which would render, we have a contradiction there, one of them couldn't be a P plus. It needs to be maximal below our surface sigma apart from its own P plus. So if we move on now to an additional space dimension, so we have 2+1 space-time, this increases the number of possibilities. We can get more than one P plus. We have a plot included here, which are a number of horizon molecules. Again, the horizon molecules being the links in red. So given that there are more P plus possible, this increases the number of horizon subcausal sets we can generate, which are all of the points that are classified as P minus and P plus. We remove all other points from the scattering, and they're not plotted in this case. It also changes the shape of the joint, which is the intersection between the sigma surface and the H light-like slice, from a point in 1+1 to the top of this light cone, this circle in 2+1 spacetime. So we'll move on to black hole entropy now. And as we said, this is the main goal of this presentation, is to find a counting prescription, which we call omega of n, which represents the number of microstates of n horizon molecules. So we know from thermodynamics that the entropy of the black hole scales linearly with the surface area. And then from Barton et al., we know that the expected number of horizon molecules gives the surface area in discreteness units. So if we take the microcanonical ensemble and assume that each microstate is equally probable, we can use the Boltzmann formula for entropy. And this is where we need our counting prescription omega. So if we examine this Boltzmann formula, we see that omega of n must be exponential in n so that it scales linearly with the entropy. And For these counting methods and labeling afterwards, and a brief summary of the presentation, I'll pass it over to Tianyu.
Okay, thank you, Ben. I'm Tianyu. I'm currently studying in NUIG in 3rd year. I'm also studying theoretical physics. Okay, back on to counting. As Ben said, because we want to find entropy that scales linearly with the horizon molecules, as we can use the horizon molecules to represent, to estimate the surface area of black hole. Yeah, so we need to count the number of microstates for a given number of horizon molecules. Yeah, so I think we first tried just from just the most simple stuff is just that we treat every point as the same. Yeah, so you can look at the diagram down there. We have like 3 different states. Yeah, so there, but now we have each state. Now we consider there is 3 horizon molecules there, and there are 3 different configurations for 3 horizon molecules. Yeah, so you can see there's the upper line is the p plus points, and the lower line is the p minus points, and you can see there's 3 p minus points for each configuration, and then you can see there's 1 p plus point on the left, and then on the center is 2, the right is 3. Yeah, this is all the configuration for 3 horizon molecules. Yeah, and for this particular counting, yeah, if we consider n equals 4, 5, 6 and make it large, and then the total number of configurations will scale with like e to the square root of n, and this is the total number of microstates. And yeah, total number of, and also you can say the total number of configurations. And this is not we wanted, because if we calculate entropy with this, then you will get the entropy is like scales with like square root of n, which is not the result we want. Yeah, and then because this failed and we tried, we also because we also tried the other types of counting, because before that it scales with square root of n, which is too slow. Yeah, so, and because we considered all the points are same, so the number of configurations is too small for that. So we try to like label and unlabel them. Yeah, so this is like a combinatorics problems. Yeah, we can like reframe it as, because each p minus points must connect to p plus point. Yeah, so we can treat p minus as balls and p plus as box. Then you can like put like you can like draw the link from p minus to p plus. Yeah, so you essentially like putting balls into boxes. Yeah, so if we, yeah, so there are 4 types of ways to count this. Yeah, so you can see there's when you can see on the table there, on the last line where there's unlabeled balls and unlabeled boxes. Yeah, then the total number of configurations is just the partition function, which is from the previous slide, which is it's growing too slow. Yeah, and then there are other ways of counting that, and you can see the sk2n there is just a stirring number. It's just a number of ways of like putting unlabeled balls, labeled balls into unlabeled boxes, and vice versa. And then, but this tool gives either it grows too fast or too slow. Yeah, and we want to focus on the first line, which is unlabeled balls and labeled boxes. Yeah, and then yeah, for that, you can see this is actually a stars and bars combinatorics problem. Yeah, and for this problem, we already have a solution, which is for a given number of p plus point, we have n-1 choose k-1 configurations, where like the n is just a number of p minus and k is number of p plus. And you can see there's more examples here. We have 2 labeled p plus and 4 unlabeled p minus points. So if the total number of configuration is just n-1 choose k-1, which is 3 choose 1. Yeah, so the total number is just 3 here. Yeah, so on to the next slide. Yeah, so okay, furthermore, because as Ben said earlier, on the 2+1 space, we can have more than 1 p plus. In fact, the number of p pluses, maximum number of p plus is the same number as how many p minus are there. So if there are n p minus points, the number of possible allowed p plus points ranges from 1 to n. So to sum up, so we must sum up all of those. Yeah, so you can see there's a summation here. So for the 1 p plus points all the way to n p plus points. Yeah, so we can see from this the total number of configuration is 2 to the n-1 power, and this is the total number of microstates that we want. Yeah, so you can see if we calculate the entropy now, it's like it scales with n. And yeah, then there's more example here, and because we have found the omega that we want, yeah, this is the good candidate for the number of microstates. Yeah, and I think that's all. Yeah, and then yeah, this is to sum up, because we started with causal set theory that is like treating space-time as discreteness, and also because we're using the horizon molecules as the to express the surface area of black hole in discrete use in the units of number of horizon molecules. Yeah, so when the number of horizon molecules gets large, and this can be challenging, like computationally. Yeah, and then because today we talk about the black hole entropy, and yeah, and then we found some labeling of p minus and p plus points that can scales correctly. Yeah, and there's more, like arises like more questions. It's like why is p plus distinguishable and p minus is not? Yeah, and then when this if you look at it in, like, if you imagine it's like each p plus has its own group of p minus points. Yeah, so we can further analyze it. Yeah, what is the physical meaning of this? Yeah, and then I think that's all. Yeah, and then we just I think I'm on behalf of the interns today. We want to thank all the staff that helped organize this internship, and we want to thank Graham and Takaki yeah, for their like talks. And then lastly also Ian, Shane, and Tenjo. Yeah. And that's all. That's all my talk.
Cheers. Thank you very much, guys. Lovely talk. Does anyone have any questions straight off? Faye, yes, there you are. Hello.
Thanks, that was great. Well, first of all, I hope that you're gonna keep working on this and write a paper. That's fantastic. Can you show that slide where I think it was Ben, in Ben's presentation, he showed the 2+1 picture where, yeah, that one. Okay, cool. So this is original, and I think it's something that could really be useful and improved on, and there's all sorts of things to investigate, and perhaps you already know them, to do with this kind of picture, which is it's kind of exactly what you want to see, and no one has seen that before, and that, you know, that picture in itself I think is worth putting into the literature. So it's exactly what you want, because you can see the molecules they're right where you want them to be, which is clustered around that circle. So there's various things to add. So as you said, we already know that the p minuses, the number of p minuses, which is the number of molecules, that scales in the right way. So the question is, does p plus also scale? The number of p pluses, does that also scale in the right way? So you can, maybe you even know the answer to that question, but I suspect the answer is yes. So you counted all possible numbers of p pluses from 1 to n, right? But if you look at that, then I think if you do this many times, you're never going to get just one p plus. So you might as well not count that. I mean, it probably doesn't matter if you count it, because the number of configurations is very small for that. So you won't be over counting. So I think it won't make any difference whether you count that or not. But another way you could flip, if the number of p pluses scales in the right way, then in some sense you could redefine the molecules to be each p plus with its set of p minuses, which is something you already pointed out. You know, there's that structure. So the horizon is made not now of the linked molecules, but of the p plus molecules. So each p plus has its little family of p minuses, and those are the molecules. And you can ask, does that scale in the right way? And you could do the calculation. I'm pretty sure you could do it.
Sorry for interrupting. What do you mean by the right way?
It scales as in this case, the length of that, the length of the circle, the circumference of the circle.
Okay.
Which in this particular, so because this is flat space, scaling like the length of the circle is the same thing as scaling with the density of your sprinkling.
Because we want to get an area at the end of the game.
The length is the analog of area in 2+1 dimension. Yeah. Right. So in 3+1, you would get a 2-sphere, and it would scale like the area of the 2-sphere. Yeah.
Thanks.
Yeah. So if p plus scales in the right way, then you have a different sort of picture of what you might count as states, microstates of the horizon. So you'd sort of think of, and this might answer the question of why the p pluses are distinguished, but the p minuses aren't. So it's like each p plus is sort of a position on the horizon, where a state can be, a local state. And then there's a number, a small set of different states that P plus can be in, labeled by the number of P minuses it has. So here, I mean, I can't quite see, but it looks like each P plus either has 1 or 2 P minuses.
Yeah.
Is that roughly it? Yeah.
Maybe a few, maybe a 3 every now and then, but
maybe a 3 every now and again.
Yeah.
Okay. So then you've got, you know, then you're counting with a particular, so you might have a certain probability for getting 1 P minus for each P plus, and a certain probability of getting 2 P minuses for 1 P plus, and a certain probability of getting 3 P, which is lower, 3 P minuses for each P plus. And knowing those, which I'm sure you could work out again, then you know how many microstates there are for a given fixed number of P pluses, which is now, in this new way of thinking, that's the number of molecules which you're fixing.
Yeah.
You can calculate the number of, you know, number of weighted with probability, the number of microstates of the whole horizon. And if all that works out, you could get something which scales exponentially in the number of P pluses.
Yeah.
This is great. It's so great. But I love that picture that I need to see more of those, generate more of those with more sprinklings and do it in one higher dimension. That would be fantastic.
How many points in total is it that you have to sprinkle again to get this many horizon molecules? Because it's kind of obscene, right? Like just to get.
Let me check. I think.
And you can imagine in the next dimension up, you know, you have to sprinkle so many just to get a nice covering of the sphere. I
think I sprinkled. How many did I sprinkle? I think it's like 2,000 points, and then I get this kind, like averaging out at 30 horizon molecules. Yeah.
Yeah.
I bet you could make that a lot more efficient, for example, because because the probability of there being a P minus dies off exponentially below sigma. I bet you only need to sprinkle. And you know where where the molecules are going to be. You can just sprinkle, you know, just a neighborhood.
These are definitely things we were considering along the way, and I think Ben also just the other day or today was showing me a graph of like essentially like the likelihood of, you know, how far down things will be so that you can anticipate you know, how far down to make these things more efficient. But yeah, they're always optimizations. But I like that idea as well, Faye. It really harks back to the, you know, labeling the plaquettes around the horizon, because here the label is like the number of P minus points or something. You know, a 1 or a 0, or sorry, a 1 or a 2, or maybe sometimes a 3, if you have 3 P minus points. And yeah, that's nice.
Yeah, and you can even draw that, you know, the color, right? Red, blue, or green, or something.
Yeah.
And taking into account that some, you know, 3 is less likely than 1 or 2.
Yeah. Ricardo, I saw you had your hand up for a while.
Yeah, but Faye answered my question.
Okay, great.
But in any case, I find it fascinating to get after microstates. And if I understand it correctly, it's like the same horizon can be described by a different probability for the P minus and a different probability distribution for the P plus. It's very intriguing, and I completely agree with Faye. I'm a fan of your papers. I never saw you before, and we have a lot of common friends. But yeah, please keep going. That's all.
Cheers. I can't see everyone. Were there any other questions? Maybe we could even go on to back to other questions for the other talks if people want to do that.
I'm sorry, I have a problem being quiet. I have a comment about William's talk and how it is interesting, not only in, I would say, in the relativistic context, but also for fluid membranes, where the issue of topology change is there. You know, we're talking about surfaces in Euclidean space, but a lot of the description that he presented may be relevant.
Do you think there's some sort of analog for the metric or something in that?
Yes, in fluid membranes, for example, we are talking about two-dimensional surfaces. The one contribution that comes in is the integral of the Gaussian curvature. That's a topological invariant. If you have that's the Gauss-Bonnet theorem. If you have topology change, it becomes interesting. And this kind of work, and I definitely like the color picture, is may be helpful in that context.
Yeah, yeah.
I'm gonna pick up the ball on that because I like the approach. Yet I did expect some matching conditions.
Matching conditions for
when you join the two spheres, or
yeah.
So I would have expected some kind of I'm going back to relativistic kind of Israel matching conditions.
Yeah, yeah. So in this case, you are taking the induced geometry from the flat background, essentially. And that's what's giving you this metric that William had at the end. So all of that is kind of
induced metric.
Yeah, yeah.
Or first fundamental form.
I think that induced metric also fails the Israel junction conditions, which are to do with it only having it not having any discontinuities or discontinuities in its normal derivative, normal to the surface, right? I think that's right. But I think in this case it fails on the latter point. But that's to do with allowing you to get a solution, a distributional solution to the Einstein equations.
Right.
Yeah. Which maybe we weren't aiming for quite yet.
But I think you guys are on the right track.
Yeah.
And I enjoy the talks. Thank you.
Cheers. Thank you. I could pause or stop the recording, and we could have a more casual discussion.
Yeah, no, I think everyone gave a great presentation, and thank you very much. Yeah, probably stopping the recording is reasonable.
All right.